So this is the first, obviously you have the schedule of the GAN lectures, and one of the things what we thought was the first few lectures would be on the fundamentals of capillarity, the fundamentals of contact angles. But one of the things I would like to talk about is the energy that is required for contact angles to move and things like that. So there would be a lot of fundamental stuff going on in the first two lectures. And then we talk about how do you modify surface properties, what are the methods where you can modify. But in the first two lectures, we would be doing some derivations, but very, very simple. It's a very basic level energy balances and thinking about, okay, if you want to fill a glass of water, how much of energy is needed for the contact line to move? Okay, it's simple things like that. Okay, so what we're going to do, and obviously as we go on, we will look into, you will see a lot of experiments, you will see a lot of modeling. One of the things I'm going to talk about is some things which are very new, which is stability analysis, especially in terms of droplets. And one of the things we'll also talk about is complexities. Complexities, obviously phase change itself is a complex problem. But you have an additional complexity because most of the industrial solvents or industrial coolants that is used or industrial liquids, they are mixtures. They are mixtures having multiple components. Some of them, they have competing volatilities, they've got competing properties, and these things can affect the way evaporation can happen. These things can affect the way patterning can be made on surfaces as well. So these are important things that we'll also look at. And we look at it from the framework of lubrication modeling, from the framework of experiments, from the framework of simulations as well. Today, I think one of my students, he's going to be giving you a hands-on session on how to put a three-dimensional droplet on a three-dimensional surface. So it is just that. And probably on Friday, how to make it evaporate. Okay? How to make it evaporate. And basically, you will be getting the solution files as well for you to look at through ParaView and things like that. Okay, so one of the things I would like to say is welcome again. You would have to bear with me for a number of days, so I apologize upfront for it. It's going to be, I'll try to make it as interesting as possible. Look at the content, don't look at me. So that might be more interesting. So before I begin, I would like to thank a whole huge list of collaborators, which I've worked on over the years. I've brought in some elements from the things I have learned from them and from the things I have learned by collaborating with them. So one of the key aspects is all of my work is with experiments, all of my work is with theoreticians, as well as all of my work is with numerical modeling. So normally any problem we would tackle in this three-pronged approach: experiments, numerical modeling, and things. I have special thanks for Halim, Rodrigo, and Glenn McHale. You would know that these are, Glenn McHale and Halim are stalwarts in capillarity and wetting phenomena. So one thing I asked them, because they are my next door colleagues, I asked them that I don't want to reinvent the wheel, I'm just going to use your notes. So some of their, you will find a lot of the elements from their research as well here. Okay, so I would like to acknowledge their work. Plus, of course, we have a number of people whom I work with. So Khalil, David Scott, this is high performance computing person, both of them, Mark Sawyer and David Scott. So we have a Edinburgh Parallel Computing Center. We have a huge national supercomputer there where we do very high density simulations as well. So Danny Orion, some of you already know, he's an experimentalist. George Karapetsis is also a theoretician whom I work with. He's based in Greece. Omar Matar happened to be my supervisor as well when I was doing my PhD long ago, but now a very strong collaborator. I work closely with Rama in Bangalore, and there we are looking at how particles move, but during phase change. As phase change happens, how particles move. So that's a very different problem as well. And Lennon, he's one of my collaborators from Dublin. He's from mathematics, and he looks into stability aspects and stability criterions and things like that. Yutaku, he was originally based in Kyushu University. Sarthak might know him. But now he's mainly in experimentation, so he has contributed a lot towards experimentations. And when we look into soft matter and when we look into aspects of surfaces and surface physics, and so I work closely with Alidad Amir Fazli from Toronto. Okay, and right up front, I would like to thank all the funders who have contributed to the research. Of course, our national UK PSRC, European Commission, the DST fellowships I have secured over the years, along with Rama and Sarthak and Parmod and everyone, and basically JSPS, as well as I was fortunate to attract a lot of industry funding as well, because there's a lot of industry problems that we solve based on wetting, based on, and also some of them, they are only interested in simulations. They're looking at how to scale up things, And of course, we have a strong collaboration with the European Space Agency, because we also look at the phenomena in microgravity. Okay, so very quickly, again, as I mentioned, these are some notes from Halim and Glenn and Rodrigo. So I'm going to be using some elements of their course here, okay, because they've already done this bit here. So the first thing I would like to talk about is surface tension, and I would like to get your ideas about what is your perspective of surface tension. When people say that, this is because of surface tension, what do you mean by that? What do you think about it? What is your opinion? There's no right or wrong answer.
It is a property of the fluid due to which the surface acts like a stretched elastic magnet.
Perfect. That's one thing. There is any other definition of surface tension? Any other definition? It could be, I mean, this is from a practical standpoint, but do you have a thermodynamic standpoint as well? Sorry?
Unbalanced cohesive forces.
Yes, cohesive forces, unbalanced balanced cohesive forces, yes. Anything from the thermodynamics point from the energy perspective?
Energy needed to bring the molecule onto the surface.
Energy needed to bring, but it's also the minimum energy that is needed for any surface to be stable. It's a minimum. So the thing is, all our systems, they would like to go into this energy well. That's where they love to be, and that's where we call it as an equilibrium. And surface tension is no different. Surface tension is basically, if you look at the unit of surface tension, it is Newton per meter or joule per meter squared. So essentially, surface tension is energy, the surface energy. And if you multiply surface tension by the area, you get the energy out of it. Okay? So very simply, surface tension is a phenomena that brings, that makes sure that, as your colleague pointed, interface that defines the structure of the interface. Plus, at the same time, it also is the work that must be done to bring the molecules to the interface. Okay, so that's the energy. But then everything has surface energy, whether it's a solid vapor surface, whether it's a liquid vapor surface, whether it's a triple point. All of these things have got a role to play, have their own energy. And if you want to deposit something on the surface, the system must be at a lower energy point for the drop to sit there. Okay? Otherwise, it will do whatever it wants. Otherwise, it will go all over the place. Okay? So one of the key things that we would look into is energy minimization. It's the lowest. So it is always, all these systems look for an energy well. Okay? So very quickly, so this is a typical definition, as many of you would already know. You've got a droplet sitting on a surface. This is a solid surface, this is gas, and this is liquid here. Typically, it will have some kind of a shape. This is the apparent so-called equilibrium contact angle. The reason I'm talking about so-called equilibrium, I'm going to be explaining later on, is because it's such a, the definition of contact angle is pretty complex. So if you look at any system, there are a few ways to look at. There are a few ways to look at the system. So one is, if you look at this particular region, if I zoom into this region, it would probably look something like this. Okay, this is where the bulk thing is. But as it approaches to the surface, you may actually have a film. Okay, so you have actually two contact angles. You have got an apparent contact angle and you've got an inner region. Okay, this is obviously this is a submicron or whatever, adsorbed layer. Okay, and that is where we make an approximation that, okay, there could be a precursor film. There could be a precursor film. But sometimes for a macroscopic perspective, for a simpler understanding, what we say is, okay, we'll just live with the macro contact angle. We'll just live with this for the time being. Because when we deposit a water droplet on a surface of our liking, it is adopting that shape, and the shape is not changing, so therefore it's probably energy balanced, and therefore that might be an equilibrium contact angle. But if you look at it closely, you might have a kind of a layer. Okay, but we are not very worried about that for this case. So simply, very simply, you will have the definition of the contact angle as defined there. So basically, it's a mass balance, it's a force balance between all of these vectors. And all you would be getting is simply this. Okay, that is cos theta E is sigma Sg. So these are surface energies of solid and gas, surface energies for solid and liquid, versus surface energies for liquid and gas, liquid vapor or liquid gas. Okay, now this is a very important definition. Now, this is the fundamental definition, and it's called as the Young's equation. And one of the things that we can do is look at several cases with that equation, just with that equation. The first thing we can look at is basically the so-called spreading. Okay, the so-called spreading is basically, if you just look at the force balance, you would get sigma Sg is on this side. You've got some sigma Lg and some sigma L. So basically, the net energy in that area would be something of this form. Something of this form. Okay. Now, if you say that S is greater than or equal to 0, if this particular number is greater than or equal to 0, this means that sigma Sg minus sigma Sl plus sigma Lg is greater than or equal to 0. That means that sigma Sg is much greater or equal to than the sum of the liquid solid surface energy and the liquid vapor surface energy. That means that this is the minimum area, this is the minimum energy configuration. And whenever you have that, okay, the combination of sigma XL and the combination of sigma Lg is, the sum of this is smaller than this, this is going to be spreading. This is the minimum energy requirement. So that is when your liquid will spread. Okay? And in an ideal case, it should spread infinitely, but it doesn't, of course. Okay, it's a complete wetting phenomena. Okay, it's a complete wetting phenomenon. So that is just the energy thing. Now, the other thing you can look at is, but obviously in reality, you never have complete wetting. You will always have partial wetting. So in case of partial wetting, typically this S is not greater than or equal to 0. In fact, S is less than 0. So if we look at S less than 0, simply what it means is that sigma Sg is minus sigma Sl plus sigma Lg is less than 0. This means sigma Sg is less than sigma Sl plus sigma Lg. Now you can have various interesting combinations. So depending upon because you already have a relationship between sigma Sl and sigma Lg with respect to contact angle. Depending upon the contact angle configurations, you can actually have a hydrophilic, somewhat hydrophilic substrate with contact angle slightly greater than 90, slightly, in this case it's less than 90 degrees, but if you have a hydrophobic substrate, you will have more than 90 degrees and so on and so forth. So you can have a balance between that. Okay? So this is just this energy argument which I would like you to think about more whenever you look at any surfaces and whenever you want to make sure that you're able to define a surface, deliver a surface which has certain wetting properties. So obviously, if you combine, probably erase this in this way, is it? No. Yeah. So if you combine these two guys, if you combine the Young's equation with the spreading equation, you'll get something like this. So basically, now your spreading coefficient is completely dependent upon the surface tension of your system, okay, Lg. Certain contact angle, this is the supposed equilibrium contact angle, minus 1. Okay. Now, I'm going to talk a bit about what is a contact angle and why do I think that equilibrium contact angle is not a perfect concept. Okay. So obviously, you've got these, you know better than me the kinds of applications these things have, whether it is paints, whether it is fabricating a very good heat transfer surface, and heat transfer is very much linked to wetting and all that stuff. Plus, fabrics is a big thing. So wetting is important in several areas. Now, if you look at certain aspects, certain properties, so one of the things we should always consider is no surface is smooth, so you'll always have some roughness. Okay, you will always have some roughness. So now, if I do a small experiment, so if I do a small experiment where I'm actually having the surface and I'm actually sucking the fluid from this droplet away. So what's going to happen is basically your contact angle is, your droplet is going to shrink. So as it shrinks, initially it won't shrink. So initially it will begin like this. Then in the next state, it might be in this way, and then after a certain point, you will have a motion. So if I plot contact angle versus time, if I plot so-called equilibrium contact angle with time, so as you keep sucking, you will see that the contact angle will start dropping, and after some point it starts moving. When it starts moving, the contact angle is almost constant. Not exactly constant, the contact angle becomes almost constant, and this becomes the so-called receding contact angle. Okay, so that's why I say that equilibrium contact angle is just based on the thermodynamics, based on the amount of material placed on the system, plus it's completely experimentally determined. Okay, there's no hard and fast rule that you can determine an equilibrium contact angle theoretically. Okay, but when you look at receding contact angle, it's the receding contact angle is the point at which the droplet starts to move as you take off more of the liquid. And the same is true when you have advancing contact angle. So in case of advancing contact angle, you're pumping the fluid into the droplet. So initially you got a droplet, you start pumping the fluid, so it's going to grow. And after some point, it starts moving. So in this case, this is the advancing contact angle, which will it will actually increase, and at some point it starts moving. So this is the point where you have theta A. Okay, so you have these two things. So generally you will have the equilibrium contact angle between the so-called receding and the so-called advancing contact angle. So this is the typical when someone says equilibrium contact angle, it's somewhere between advancing and receding. Okay, and obviously there's so many definitions, there's so many ways in which you can interpret this. So one of the ways you can interpret this is, okay, so if I have this droplet and obviously it is moving because it started moving, it has departed from its equilibrium position and it started moving, how much of energy is required, how much of force is required? It's basically sigma LV. This is the difference between advancing and receding contact angle. The actual difference between, if I call theta A minus theta R, this is the so-called contact angle hysteresis. Okay, this is the so-called contact angle hysteresis. But again, you can use the contact angle hysteresis or the definition of cos theta R minus cos theta A to define the so-called force. That is you would say that some sort of a force that is at least required to pin the droplet, or if you go beyond that, it might start moving. Okay, some sort of a force which is there. So basically, this is from a physics standpoint of what exactly can be learned from advancing and receding angles. But again, nothing of this is perfect. This is just an observational. And putting these observations into some sort of a mechanistic approach. Okay, but of course you would always know that no surface is smooth; it has a rough surface. So there would be pinning. Most of the time there would be pinning at all points. Okay, you may have an initial small movement, then it stops. Then you might always need to have more amount of energy because the roughness is a bit sharp to make it move again. So obviously the stuff I'm talking about is a very approximate way of looking at things. Okay, now one of the main problems is basically what is happening at the contact line. Now why does a contact line move? Okay? Why does a contact line move? So normally when you look at even simulations or theory, when we look into a problem which has a contact line, it could be a film or it could be a droplet, the first thing we apply on the wall is the no-slip boundary condition. A no-slip boundary condition means whatever is there on the boundary is stuck to the boundary, or it has the same velocity as the boundary. Okay? And if you have a droplet which is suddenly decided to move, it's a bit weird. You have a no-slip boundary condition. Why should it move? It's defying the thing. This is actually called as a contact line singularity. Now, and this has been a debate for so many years. And I should say that it's not yet resolved fully. Okay? There are various ways. So that is the flaw of the modeling approaches that we use. Okay? So whenever you have a triple phase contact line, you need to have special considerations at the contact line boundary. Okay? It is not fully, it's not completely no-slip boundary condition. At the interface, people do apply a slip condition. It's called as the Navier slip condition. And you've got all these weird definitions, artificial definitions. I would say, if people use a slip length model, Navier slip model, I'm sorry, but I don't agree with it. Okay? Because Navier slip model has a slip length, and slip length is anyone's choice. Okay? If you're doing simulations, if you keep increasing your mesh resolution, you will reduce the slip length. Okay, so there's no standard phenomena. There's no way you can define a slip length. Okay, this is the slip length I want. It's very difficult to do that.
Experimental microfluidics, they try to determine the slip length?
Yes, they do determine the slip length based on the surface. But again, it's so dependent upon the surface structure. So what people do is typically they take experiments, they take the slip length and put that in the Navier slip condition. Because the experiment showed that this is a slip length somewhat. Which is somewhat okay, but it cannot be a generalized thing. It cannot be. In another sense, what you can probably do is, this is probably, I'm going to be covering it on Friday anyway, is there could be another approach. Another approach is, if you look at the contact line, this is my liquid, this is my vapor, this is my solid. So one thing is, you've got an energy balance between this guy and this guy here. If the energy in this side is greater than energy on this side, this guy will move, or vice versa. Okay? So one way to look at is to understand the energy balance between the two. And you can have a no-slip boundary condition, but the energy boundary condition will make sure that that is able to move. Okay? So what you can do then is basically say, we can use van der Waals, because this is a very, very local phenomena. We can use van der Waals and couple it with DNS. It's called as the Kahn-Hilliard model. Okay? It's called as the Kahn-Hilliard model. And what you can do is you can get an energy interpretation very close to very close to the wall, which will obey your no-slip condition, but at the same time allow for contact line motion. Okay? So that is more from the energy perspective. So that's why I prefer the Kahn-Hilliard model, because at least I don't need to make approximations on slip lengths. The physics are generally there. The only thing I need to be worried about is there are things like mobility parameters in van der Waals equations. And those equations are generally there for certain liquids, certain gases. These are properties of the liquids anyway. So if I'm able to get those things, I'm just going to put them there. Yes?
The energy that you talk about here is the surface energy only, is it?
It's the surface energy.
Okay. Because if the energy is high on the left, why should that surface increase further? Because it should minimize.
Yeah. No. So based on the condition that you give. So if you have your system wherein you have a heated surface, and you got a very thermally conducting fluid there, then or maybe you have a thermally insulating fluid there. So there's a lot of energy which is here pent there. So this has an effect on the side which is immersed in the liquid. So in that aspect, so you can change these things. But of course, if you have a constant isothermal case, it should just remain like that, because there's no force which is trying to push it anywhere. Okay? So this is when. And also, when we talk about energy balances, one of the main things that drives the motion of motion of the droplets is also an instability. And those instabilities can be thermal, they can be hydrodynamic, they can also be surface tension. Okay? So we'll also look into the instabilities that can drive the motion. Okay? So, and those which cause that energy imbalance between the two sides. Okay? So one of the things we can look at is how do you determine energy at the contact line? So if this side is say X and this side is say Z, then typically the viscous dissipation. So this is the contact line. Okay? So this is the contact line very close to the surface. So typically the energy dissipated because of viscosity is something like shear stress times gradient of velocity, something like that. It's just a, okay? So this is the energy that is there. So basically if you multiply this energy by area, you'll get force per unit length. So anyway, so what I'm going to do is if you look at tau dot grad u, I'm going to write this as mu del u by del z. This is just one dimensional. And because this is one dimensional, you got a velocity profile. There could be a velocity profile there. I don't know whatever velocity is there. There could be a del u by del z here. Okay? So you would have mu del u by del z times mu del u by del z. And obviously, you would have it on this area. So this is an area parameter. So you would have some kind of a dx, some kind of a dz, and that is the energy that is there. Okay? So if I want to calculate the energy that is dissipated at the contact line, it is something of this form. It is something of this form. So if I want to find out the whole picture of it, if it's a big infinite solid, I'll have this double integral which is going from 0 to infinity, dx, I'm doing the dx there, and I bring all the dz terms there, and this is going from say 0 to the height of the contact line, h, something like that. Okay. Now if you do that, then basically what is going to happen is, and again, this is something which we need to be very careful about. And many books, they think that the reader is able to guess this right away. This particular contact line, in my opinion, is not the apparent contact angle. It's the inner contact angle. Okay? Because if you want the droplet to move, if you zoom this in, this is going to be like this. This guy has to move. This guy has to move. So technically, the contact angle, the inner contact angle is always very small. This is the apparent contact angle, which we call as the equilibrium contact angle. But this is the actual inner contact angle, which is very small. So if you look at this, this is probably of the order of less than 1 degree or probably close to 1. Okay? So, and what you're looking at is this region where this height is, say, h. This is the film height. This is the precursor film height. Okay? So if you look at this, so if I look at this triangle, so this is looking like this is like your so-called theta, whatever is there. Then if you look at tan theta, this is basically h by x, but theta is so small, so this is actually equivalent to theta. Okay? Because theta is so smaller than 1. Okay? This is not the apparent contact angle. You may be on a hydrophobic substrate. Even if you are on a hydrophobic substrate, you will have the contact line could be like this. And what we are looking at is this region. So okay, so this is where we are. So theta is approximately tan theta. So that means that h is approximately equal to x theta. So if I substitute that, I can put h as theta x into the limit here, and obviously you got this du by dz, and du by dz is approximately u by z. It's again an approximation. So we are just doing a scaling argument here. So if you look at this, erase this way. So if you look at this, all I'm doing is basically trying to integrate this first. So you'd get 0 to theta x. Del u by del z is basically u by z, so that went there. And this is, obviously it is dz by z squared, so which is equivalent to 1 over z. So this is, you'll get something like 1 over x if I put the limits and all that stuff. Okay, you'll get something like this. Now what I'm going to do is I'm going to resubstitute this back, so you'll get mu u squared by theta, and you'll get something like dx by x here. Okay, when I put it back into the energy thing. So when I put this back into the energy thing, you'll get something like log ln, and here this is going from actually this is going from 0 to infinity. I'm putting it for a finite length. So this could be the length of the precursor film, for example. So you would have something like this. So you'd go from 0 to L or whatever, any L, I don't know. Okay, and rather than going from 0, I would just say at any A here. So A to L, so this could be A. A can, if A goes to 0, so when you approach the contact line, what do you get? Energy becomes infinity. Okay, so that is the main contact line instability problem. So this is the energy, based on the energy, you'll have a contact line conundrum, which is basically saying that you cannot move anything. If you have a droplet sitting on a surface, the so-called physics here say that you cannot do anything. That's why there was this big statement which says that not even Hercules could sink a solid. Because typically you would require infinite amount of, so if you want to sink a ship, it should not be possible, because you would require infinite amount of energy to make sure that the contact line should move so that the ship can sink. But obviously not. We know that everything sinks. Okay, so that is one of the problems. So, so the contact line conundrum is therefore the origin of one of the main numerical as well as theoretical issues when we try to model it. Okay. Any questions so far? Yeah.
Why wetting has cos theta not sin theta?
Which one? Sorry.
So why wetting has cos theta not sin theta?
I mean, it's because it's just you can have sin theta as well. It depends upon the angle and side you're taking it. It's up to you. But typically, because when we put surfaces, we put surfaces on the forces, we do a force balance on the surface. But if you do vertical force balance, so when we do interfaces and we have to have a vertical, then you will get a sin theta. So it's just a matter of direction. Okay, so obviously, so that is one of the problems, and this is, so what people do is obviously theoretically you know that there is a problem at the contact line, so we have other means of doing it. I'm going to talk to you later about that, but one thing we look at is molecular dynamics. Okay, the molecular dynamics looks at the molecular level systems at the contact line, and you can see what causes the jump and what causes that, and typically you would get, I mean, this is the so-called molecular kinetic approach. You would get, I mean, there's no derivation here. I don't want to derive this because this is completely based on MKT, based on the Boltzmann equation. So the amount of time fluid 1 takes to hop to fluid 2, or rather this contact line takes time to hop to fluid 2 is typically defined by this, tau. Okay, we don't have to worry too much about how is this coming. You can see that this is a force here. This force is due to the surface tension. This is the driving force per length there. Okay, and because this is a function, this is time, and you have a contact line, so-called contact line velocity u, or the length lambda, you can calculate the contact line velocity is lambda over tau. Okay, and you can get some sort of a contact line velocity as well. This is the molecular kinetic approach. We are not too much worried about it, but this is just and we know for sure whenever you have such molecular kinetic approaches, these are talking more about a very slow phenomena. Okay, the very slow phenomena. So if you have a rapid motion of a contact line, so for example, when you have boiling, you can have almost an explosive time, in an explosive time scale, you have a motion there. Those things are not valid here. Okay, so this is from a very slow molecular kinetic approach that you would get some sort of a contact line speed, and again, this is from there. But of course, not everyone can deal with molecular kinetic approach. Okay, you need to have continuum physics. You want to develop your surfaces and all that. You need to have that. So this is just a kind of a explanation about what is the molecular kinetic approach. We also talked about measurements of contact angles. I mean, Many of you are experimentalists already, so how do you measure contact angles? Sorry? Goniometer. But what is the method that you use? I mean, say that if you want to identify so-called equilibrium contact angle of a certain fluid on a certain substrate, what would you do? Would you just deposit, or there are different methods? You have also a plate dipping method, isn't it? You've got the Wilhelmy plate dipping method. And then you can analyze it, and then you can get, okay, this is, but you can use the Wilhelmy plate dipping method also to calculate surface tensions. Okay, so you'd use these goniometers and all that. And typically, when you have motion, you, as we already talked about, you have an advancing angle and you've got a receding angle, and the difference between the two is the so-called contact angle hysteresis. Okay. Now, what we're going to do is we're going to look at the shape effects of a droplet. And here, what I will be doing is I'm going to be doing some derivations based on, or rather, modeling some based on basic energy concepts here. Okay. So the first thing what we're going to look at is looking at a simple droplet or a bubble. Okay. Simple droplet or a bubble. What shape does it adopt, and why does it adopt that? Okay, we're going to look at that, and slowly we'll also look at quite complex surfaces, especially when if you have two parallel plates and you've got a liquid bridge between the two, you have this Delaunay surface. So what is the shape of that surface? What effects does it have in terms of the force? We're also going to look at that. So we're going to look at these two cases now. Okay. So this is Alt tab, right? It's going to the. Okay. Quickly. Okay, so what we're having is, obviously we're having a drop. Let me see if I, yeah. Stylus, this one, yeah. So we're having a drop. Okay, we're having a drop, so this is say P drop, and this is obviously P gas. Okay, and this is, the pressure is obviously applicable onto the droplet. Okay, and it is applying throughout the entire volume, and the droplet is also applying pressure. Okay, the droplet is also applying pressure, and obviously what you also have is the surface tension which is holding the droplet. So you've got sigma LV, okay, the sigma LV, and let's say that the radius of the droplet is about r. Okay, so one of the things that we need to look at is, if you want to maintain the shape of the droplet, you need to understand, if it expands, how much of work is needed. If it contracts, how much of work is needed. And we have to minimize the amount of work can be done. Okay? So basically, I can write this as, so if the droplet expands or contracts by a certain amount, so if expansion / contraction by dr, that means that this is either shrinking or this is either expanding. It doesn't matter, whichever way it does. So one thing you can do is you can look at the energy balance. The energy balance can be, so if it contracts by dr, its volume is contracting, its area is contracting, everything is contracting. So I can write the work done, or basically the energy that is spent, as something like, the first thing is P gas. So this is an energy. So this is in terms of joule. So one thing I can write this as, it's something like P gas times dV. So PV kind of work. Okay, PV kind of work, and this is basically V gas. Okay, so obviously if it shrinks or if it expands, you've got the same amount of gas which is being displaced. Okay, the other thing that will happen is basically, and the other thing that can happen is the liquid side as well. So or the drop side as well. So the drop side, you will get P drop dV drop. So if the drop shrinks by dV amount, the gas also shrinks by that amount. So I'm just going to put, in terms of the directions, if I put this as minus, and then what we'll have is we'll have the surface tension acting on this surface area. So obviously as it contracts, there is a change in the surface area, which is A, dA. So I can write this as plus sigma LV dA. Okay. Now I'm going to simply mention here. So we know that if you expand it, you're shrinking the amount of volume of the gas by that amount. Okay. So basically I can write this as dV gas equal to minus dV liquid. It's dV essentially. Okay. And it's the same as dV. So if I write this, then I can write this as dE equal to P gas minus P drop dV plus sigma LV dA. Okay. Now obviously this is a sphere, so volume of a sphere is 4 by 3 pi r cubed. So this means dV is going to be 4 by 3 pi 3 r square dr. Sorry. So 3 and 3 will get cancelled, so simply you'll get 4 pi r square dr. Similarly, dA is going to be, so area of a sphere is 4 pi r square. So this means dA is going to be 4 pi 2r dr, that is 8 pi r dr. Okay. So we're going to just substitute that. So we'll just get dE therefore is going to be P gas minus P drop. dV is whatever that is, 4 pi r square dr plus sigma LV dA, which is 8 pi r dr, something like that. Okay. Now obviously this is the change in energy, and basically at equilibrium dE should be minimized. Okay. So essentially what you will have is dE is tending to 0 at equilibrium. So if you do that, then I'll be simply getting something like, I'll probably go to the next page. Right. So I'll be getting something like, let me just see what is there. So I'll be getting something like PD minus PG 4 pi r square dr equal to something like sigma LV 8 pi r dr, I think, yes. Okay. So you can see that several terms will get cancelled. There is a 2 sitting here, and so on. Pi will also get cancelled. Okay. So you would simply be getting something like PD minus PG equal to 2 sigma LV by R. Okay, something like this. This is the so-called Young-Laplace equation. Okay. Now this is a very neat equation which says that the pressure in the drop or a bubble, whatever it is, if it has to maintain the shape, the pressure inside should be greater than the pressure outside. It just says that. Okay, there's nothing else to it. Now, and this is basically a sphere. The radius is the same in no matter which direction you look at, but not everything is a sphere. If you look at oil and water emulsions, you can have shapes of all sizes, or of all shapes and sizes. Okay, so you can have ellipsoids. You can also have ellipsoids within an ellipsoid. You can have these complex shapes. Okay, so in fact, when we did oil and gas experiments, we could see shapes which look like this, and they are three-dimensional. Okay, and for some reason there is this constriction. I don't know why. Okay, so obviously when you have complex shapes, you can't have one radius. You will have probably one radius which is looking at this, the other radius which is looking from this side. So you'll have two radii there. You will have two radii there. So in general, what I can write this as is something like delta P, that is the pressure difference, is 2 sigma LV 1 by R1 plus 1 by R2, which is called as the curvature. Okay, so the curvature, in general, it is represented as 2 sigma LV. In some books, it is represented as kappa. In some books, it is also represented as H. Okay, so this is typically the the way, this is the general formula for the Young Laplace equation. Now, there is another twist to it. So the other twist is typically in some books you will find the definition of kappa as half 1 over R1 plus 1 over R2. It's almost the average of the two radii kind of a thing. Okay, and this is also fine. There's no problem with it. It's just the way you want to put your 2. And this is so-called mean curvature. Okay, so-called mean curvature. So one of the first things is obviously looking at surface tension, looking at what makes, if you have a drop of liquid or a drop of liquid in oil, drop of water in oil, or a drop of liquid in a gas, what makes it spherical? It's the surface tension. Okay, it's the surface energy which makes sure that it's spherical on all sides. There is another question. So say that if you have a liquid filament, so basically if you look at oil gas flows, so you've got oil flowing here, and you've got natural gas flowing there. So obviously there is an interface, and these interfaces, they can develop into a wavy form, and some of these waves can form these filaments and ligaments. Now if you look at this section of a ligament, it's basically like a cylinder. Okay? If you have surfactant within your oil system, you'll always have some sort of a surfactant. You'll have longer and longer ligaments because surface tension actually drops when you have a surfactant. Depends on the type of surfactant there. Okay? You'll have longer and longer ligaments. That means that pinch off is becoming more and more difficult. Okay? In some systems you would want pinch off to happen. In some systems you don't want to have it. So you can actually tune it by surface tension. Now if you look at this, if you look at this particular filament, if you look at this liquid filament, if I take a cross section like this, if I take a vertical cross section, you will just get 2 lines. Okay, this is vertical cross section. Vertical cross section, okay? If you take a horizontal cross section, the horizontal cross section has got only 1 radius. So here, R1 is some radius, I don't know what that is, radius, okay? Here, R2 is infinite, okay? This particular, so basically in this case, your curvature is simply 1/2 of 1 by R for a cylinder, okay? So what we can do now is we can actually go towards, let's do another case. Let's do another case where you can have a flat interface. Okay, so if you have a completely flat interface, like this bottle here, and you've got a very flat interface of liquid. So if you have a flat interface, so this is liquid, this is vapor. Okay, if you have a flat interface, both R1 is tending to infinity, R2 is also tending to infinity. Okay, so what would happen is if you look at the Young Laplace equation, it is basically delta P is 2 sigma kappa kind of a thing. So this is 2 sigma half of 1 over R1 plus 1 over R2. What will you get? You will get delta P is 0. Delta P is 0. So that means that P liquid is equal to P gas. Okay? So that is when you have a flat interface. Yes? Yes, yes, yes.
But delta P is not, right? Because P from outside is same everywhere.
Yeah. So, but if you look at the filament, you got the pressure inside the filament versus pressure outside the filament.
Yes, and there is no motion within the drop. So
there could be motion in the filament. So actually, usually there is a rotating motion.
But is this case representing the statics or
Statics. It's a static case.
So delta P is not a function of where we are on the drop, right?
No.
But right side appears to be a function of where we are because the
Yes.
curvature.
Yeah.
Where, like,
So in general, yes. So when we do a simulation, you got delta P as a function of radius of curvature at that particular point.
but then that will give motion to the liquid.
It will. And in fact, when we look at statistics from a statics point of view, if you want to develop a very simple model, then we can ignore that. Say that if there is no spin in the filament, and typically if you have a highly turbulent flow, the spin in the filament is very small. The filament keeps stretching in one way, and sometimes it becomes almost a doesn't go to a so-called steady state, but you will see that the filament is, the rotational motion of the filament is pretty stable. So in those things, we can assume that. Okay? So if you have a perfectly flat interface, you can see that P liquid is equal to P gas. Okay? Now, the thing is, if you look at what I had mentioned before, this is P liquid or P drop minus P gas. Okay? And if you want to be in a spherical system, the P liquid or the P drop must always be greater than P gas. Okay? When you have a flat interface, P liquid is equal to P gas. But do you think that there could be systems where P liquid is less than P gas? Do you think there could be systems where P liquid is less than P gas? I mean, I'll ask you to do a small experiment. How much time do we have? Okay, we've got 20 minutes. That's good. So, so if you take two plates, put some water on the plate, okay, two metal plates, and try to stick them together. So the liquid is sandwiched between the two plates, and then try to separate them off. Is it easy or is it difficult? It's pretty difficult. It's pretty difficult. Your film is very thin, your filament is very thin, but it is holding the plates together. Okay? And and I'm going to show you the systems where P liquid is less than P gas. Okay? So these are the so-called Delaunay surfaces. Okay? So if you look at a Delaunay surface, so you've got two plates, and you've got a liquid bridge which is there. Okay, you've got a liquid bridge. So obviously from the top view you can see that it's actually a circle here. There could be a circle. You've got a filament which looks like this. So you can see that you have one radius R1 here, and probably there is another radius R2 or R here. Okay, that is forming the kind of the curvature of the filament. Okay. What I would do is I would say that this is R1, and if I'm looking just at this, so this is R1, so let's call it this as R1, and then this one is R2, or R, whatever you want to call. Okay, and you can see that typically R1 is much greater than R2. This is obviously an exaggerated image, but R1 is typically, so if you have these plates, you have a huge amount of liquid there, so it has a wider radius of liquid, but then if you pull apart, you got a very less amount of curvature. Okay, try to pull apart. Okay, so what we can do is we can again see the energy balance. We can see the energy balance. So one thing we can say is, so R2, if the modulus of R2 is less than modulus of R1, that is just the values of R1, then what you will find is 1 over R1 plus 1 over R2 is actually negative. Okay. So here modulus, I'm just taking the values, but essentially what you're having is you're having R1 which is pushing away, that is in the positive direction, and R2 which is actually in the other way. So they are negative. Okay. So if you look at this, what you will have is, if you put that back in the Young Laplace equation, you will find that PL is less than P gas. Okay, so that is the pressure in the liquid is less than pressure in the gas, and that is the reason why you have adhesion. So this is the reason why you have adhesion between the two plates. So you will have adhesion. So this is a critical adhesion criterion. And this is how also geckos, they can actually stick to the surfaces. They can stick to the walls, and you can know that, I think it was Shivaji who used a gecko to pull himself up on a wall. That's the story, but anyway, let's believe it. But geckos do that. They can stick to themselves to the wall, and they have extreme force of adhesion. And that's because of probably this. Okay? And obviously for geckos' feet are viscoelastic. So you also have this elasticity role to play, but essentially that's because you've got this suction happening there. Okay? The other example which I can give is, if you go to a beach and if you construct a sand castle, you should have some moisture in the sand castle. And it's the moisture which holds the castle together. If you have a lot of it, it will fall down. But you need to have that optimum amount of moisture to hold the sand castle together. But ultimately, as things dry off, you get to the state of high entropy and it will fall down. Anyway, so, okay. Okay. So now, if you look at this particular case, I'm going to do an energy balance on this particular problem. So what we can do is, I'm going to go to a different page and hopefully draw a better diagram. Okay. So you've got these two plates. Okay. You've got this. You've got that. I'm just looking at one place. This is sigma LV here. Okay. I'm just going to look at one side. The gas pressure is applied onto this plate. Okay. This is P gas. The P gas is also going on from here. So you also have gas pressure applying onto that side. Okay. Let this so-called equilibrium contact angle be theta E. Okay. Let this be R. Okay. Let this be R, and let this particular height be h by 2. Okay. Let's think about that, and let this be R. Okay. In some books, they also take the whole thing as R, the whole thing as R, but it doesn't matter much for us. Okay. So the first thing what we can do is we can do a force balance. We can do a force balance, and what we are doing is we are doing a vertical force balance. And this is where your question about when do we use sine theta comes into picture. So here we are trying to pull the plates apart. So we are not sliding them together, but we are pulling the plates apart. So here you will see that sine theta E or whatever coming into picture. So if you took at the first one, so first one, say F1 is gas at the top surface, okay, top side of the surface, top face I would say. Gas at the top face would be something like, obviously this is per unit length, so I can write this as minus P gas into some length L, whatever that length of the plate is. Okay. Gas at the bottom face, that is F2, is going to be the gas it is length minus the area occupied by the liquid. So this is going to be something like P gas L minus 2R. Okay, so this is the P gas into L minus 2R. Obviously, you've got liquid which is applying the pressure as well. So you've got liquid which is applying the pressure, which is in 2R, which is over the entire surface. So F3 is going to be liquid at the bottom face, is P liquid times 2R per unit length. So we're not worried about the length scale, don't worry too much about it. And obviously, there is the surface tension which is playing a role. So the surface tension which is playing a role, it's going to be something like LV, and this is applying, this is theta E. So if I do sine theta E, it will be the force applying to that. So F4 is going to be something like, and it's applied on both sides. So it's not sigma LV times sine theta E. It's going to be 2 sigma LV sine theta E. And obviously, this is going in the opposite direction. So this is going to be minus. Okay? Because theta is in this direction, so sigma LV is going to be in this direction. Okay? So if we add all of these forces together, so net force, say chi, is equal to sum of all forces. So that is F1 plus F2 plus F3 plus F4. F1, F2, what is F1? I think it's going to be something like P gas minus L. Then you got plus P gas times L minus 2R plus P liquid times 2R. And then you would probably have something like minus 2 sigma LV sine theta E. Okay? So if I bring all of these terms together, P gas terms, so we'll get P gas times plus L minus 2R, so minus 2R, plus P liquid 2R minus 2 sigma LV sine theta E. Okay? So I can write this as 2R P liquid minus P gas minus 2 sigma LV sine theta E. Okay? So this is your net force balance. And say that, and obviously you know what's your Young Laplace equation. So Young Laplace, but the Young Laplace equation gives Pg minus PL equal to, what is that? Sigma LV by R. Okay, so we can substitute all of these things here, and what you will get is, is it correct? Yeah. So if you substitute all of these things here, you will get your net force, chi, as something like 2R, R will get cancelled, you'll get sigma LV divided by R minus 2 sigma LV sine theta E, something like that. Okay? So R will get cancelled, and if you go to the next bit, you will simply get chi is equal to So I actually converted cos theta into another term as well. So hold on, I'm just going to do that quickly. So chi is equal to, I'm going to start from this place, which is 2R P liquid minus P gas minus 2 sigma LV sine theta E. This is where we started from. And then you get Young Laplace as P liquid minus P gas. P liquid minus P gas is equal to minus sigma LV by R. This is my usual Young Laplace equation. So if you do this, I'm going to convert this R into some sort of a height. You had a height there. So I'm going to say, if you look at the diagram, so you had this height like this, you got R in this way, and you got h by 2 like this. So if you just use simple trigonometry, what you will find is that you will find that cos theta E is equal to h by 2 divided by R. Okay, h by 2 divided by R. So from here, I can get R is equal to h by 2 cos theta E. So I'm going to substitute everything there. And if I combine everything together, I would simply get chi as equal to something like 2R times, I'm substituting this, minus 2 sigma LV cos theta E by h. So I'm interpreting everything in terms of h here. And then I'm having this term already, minus 2 sigma LV sine theta E. Okay? So this becomes something like minus 4R sigma LV by h cos theta E minus 2 sigma LV sine theta E. Okay, this is just the net balance. This is the net balance. So if you look at this equation here, ideally, if your net forces are equal to 0, both of these are balanced. Okay, that means that the liquid bridge is going to remain in that way. So if you do that, so if chi equal to 0, what you will get is something like 4R sigma LV by h cos theta E equal to something like minus 2 sigma LV sine theta E. Okay? So if you bring everything together, you will get something like, you'll get sigma LV getting cancelled, and you'll see that there's a tan theta E term. You will get something like h by 2, that is the height between the two plates, is equal to something like minus tan theta E divided by R. Okay? So this is basically the condition for you to have a stable liquid filament. This is the condition for you to have stable liquid filament. And you can clearly see that there is an interaction with the contact angle here. Okay? So these are just based on energy balance concepts that you can actually look at. How much time do we have? I think we are nearly done. Any questions? Sorry, I just went on an autopilot. Yeah.
In the previous slide,
Yeah.
you took this formula h by 2 by r equal to tan theta.
Equal to cos theta.
Equal to cos theta. Can you please tell how?
Yeah, so basically it's, so if you look at previous, I think. So if you look at this, so the angle here, or the angle here, depending on whichever way you look at, this is theta E. So if you form a triangle, with this is h by 2, you can get that.
Yeah, but you're assuming that this is a circular arc.
Yeah, I'm assuming that we are in the center. Yeah.
This is an approximation.
It's an approximation. And basically, all I'm doing is I'm trying to get the minimum criterion for you to have a stable filament. Okay?
Yeah, but in general, this profile is some different curve, right?
Yeah, it can have a very sharp curve. I mean, yeah.
This profile.
Yeah. In general, it will have a very different, it can have a, usually it has a circle, it has a curvature. It has a curvature. Yeah.
This is an approximation.
It's an approximation. And moreover, it's a three-dimensional thing. So
I think angle between the center and that, if you draw a radius from the center and the line joining that contact point and the center, the angle between that should also be theta e.
theta e.
Because angle between two perpendiculars, they should be the same, right?
Yeah.
So if we assume that it's a circular arc, then it is fine. Right?
No, otherwise also I think
Otherwise, you cannot take r as constant over this entire.
Yeah, I mean, typically you will, if because these are so close to each other, you probably will have a constant R. Okay, because they are very close to each other. Because normally when we look at filaments and when we look at liquid bridge breaking, they're very close to each other. So in that approximation, you can, yeah. Okay. So good. So any questions? So sorry, it's yeah.
So the conundrum that we spoke about earlier, right? Is that the problem with the continuum approximation that we are all the estimation that you did, energy estimation, it is based on the continuum?
Yes, that's the problem with the continuum. That's the problem with the continuum approximation. Okay, and so the continuum approximation will break at the contact line. Okay, and that's why we need to have some sort of, when we look at numerical models, or when we look at theoretical models as well, we need to have special considerations. So on Wednesday or Thursday, I'm going to talk about lubrication theory. So lubrication theory assumes that you got this precursor film. So when you have a precursor film, you're not having a contact line. You're essentially sitting on another fluid. You're sitting on the same fluid. So essentially, you don't have the issue of the energy going to infinity there. So while having a precursor film is a mathematical device, as I'll employ then, actually in experiments we do find that there is an adsorbed film. So precursor films are not a figment of mathematical imagination. They can be there. If you have a highly volatile system or a mixture of liquids which has highly volatile components, the volatile components actually settle down on the surface and they form the precursor film. And it is determined, but thickness is determined by the Hamaker constant. So we do have evidence that if you do interferometry, and you'll see that, we do have evidence that even in atomic force microscopy, you can see there is some sort of a liquidy layer. Okay, that's the film. Yes.
Sir, but do we have mostly boundary condition in the precursor film also? Because there also we will
Yes. Yes. No slip boundary condition will be there on the precursor film. But the droplet is sitting on a precursor film. So from the droplet perspective, it's not feeling the surface. Okay?
And when this droplet is sliding, is the precursor film also sliding or it's stationary?
Oh, that's a very, very good question. So in principle, yes, it is sliding. But depending upon if you have a hydrophilic system, you have a longer precursor film, and we assume some physics in the precursor film because experiments have shown that precursor film doesn't really change much. So we can say that there is no velocity, there's no real movement in the other assumptions I'm going to show you is that the precursor film will not evaporate or condense. So it's not completely true, but that is an assumption that we make. So that we have a constant thickness there. Okay. Any further questions? Yeah. Sorry? F4. Oh, I forgot what is F4. Oh. It's surface tension, vertical component of surface tension. Yeah. It's 11:30. So I think we have a computing session now, right? Yeah. So in the computing session, I think my student is just going to talk to you about depositing a droplet. I don't think you would be playing much with the code, but you will be able to see the code. But I think he's going to allow you to operate more on the post-processing aspect.